Okay, before we really get into derivatives, we need to talk about the average rate of change of a function. Anytime you see the words average rate of change, you should be thinking slope. Okay, average rate of change, you should think slope. So, if they ask us for the average rate of change for this function over an interval, these are x values. Okay, -2 and 3 are x values. That's the interval. So to use slope, we've got to know the y value. They don't give us the y values. We have to plug them into the function and find them. So this is good review right here because they are going to expect you to do this without a calculator. F of -2 would be that negative in front of that x cubed stays. Okay, we've got to apply that after the exponent. So -2 cubed is -8, but there was a negative in front of it, so that's +8. And -5 times -2 is +10, so the y value here is 18. And f of 3 equals -3 cubed minus 5 times 3. So that one's -27, because 3 cubed is +27, but then you apply the negative. Minus 15. So that's -42. So we have the y values, we have the x values, so now we just need to calculate the slope over the interval. So you can do it in whatever order you want. Now I'm going to label it average rate of change because they didn't ask us to find the slope, but that's what average rate of change is. It is the slope. So I'm going to use my slope formula here. Y2 minus y1 over x2 minus x1. So -42 minus 18 is -60, and 3 plus 2 is 5. So the average rate of change of this function over this interval is -12. Now, had we selected a different interval, not -2 to 3, maybe -7 to -4, or 3 to 5, you would have gotten a different answer, because the average rate of change is talking about, well, what's the average slope between these two x values? What's the average slope of this curve? So it depends on where on the curve you're at. We're talking about a cubic function here. This is just good review. It's a negative x cubed. I don't know exactly what it looks like, but I do know that it's something like this. You need to know the end behavior. Cubic function, they go in opposite directions. It turns twice, and the negative means that the left side is going to positive infinity. So just looking at that, over here on this side, it's a lot steeper than, say, this part of the graph. It's not nearly as steep, or even the middle part of the graph, it's not as steep. So your average rate of change is going to change depending on what interval you're talking about. Okay, so that's average rate of change. Let's talk about the derivative. Okay, let's talk about finding the derivative of a function. So we covered the limit definition. You should have that in your notes from last week. The limit definition. So the first part of the limit definition is f of x plus delta x. Okay, so remember composition of functions from pre-calc? That's what that's referring to. You've got to plug x plus delta x into the function. And then we're going to plug it into the limit definition. We're going to simplify algebraically. Almost every single time, you're going to factor delta x in the last step and evaluate the limit. And so that means you're going to plug in 0 for delta x. And the result is f prime. So it's very important that we stay consistent with our notation here. So you need to try and keep things very linear. If we're trying to find the derivative of f of x equals -5x, we're trying to find the derivative of -5x. So step one was, first of all, we need to find f of x plus delta x. So what that means is we take our function right here, -5x, and we replace that x with x plus delta x. Now, we're going to need things simplified eventually, so we might as well go ahead and distribute that -5 because we're going to need that in the problem. Okay, so let's set up the limit definition. F prime of x, the derivative of x, is equal to the limit as delta x approaches 0. And I'm just writing the general term right now, okay, or the general definition. F of x plus delta x minus f of x all over delta x. You've got to know that limit definition. Okay, so let's plug in what we know. So f of x plus delta x, we simplified to be negative 5x minus 5 delta x. Then it's minus, and I'm going to put a set of parentheses because I've got a minus. Anytime I have a minus and a function's going to follow it, I need to put a set of parentheses because most of the time I'm going to have to apply that negative to more than one term. Now in this case, it is just one term, so the parentheses aren't that essential, but most of the time those functions have more than just one term. Okay, so I took my f of x function, plugged it in right there, and it's over delta x. So let's simplify. We still haven't done anything with the limit. Okay, we still have not touched the limit there, so that part is still there. All right, if we apply that negative, we're subtracting a negative number, so that turns out adding a positive. We've got negative 5x plus 5x here. That goes away. So we've got, right here we have negative 5 delta x over delta x. Well, what happens to those delta x's? We can cancel those. So we've got the limit as delta x approaches 0 of negative 5. What was the limit of any constant number? That constant number, okay? So it turns out that this derivative is negative 5. Well, let's go back to what we said the derivative was. The derivative is the slope of the tangent line. Okay, the derivative is the slope of the tangent line. Well, if this is a line that is tangent to a line, it's kind of weird, but it is that line. So pretty much what we're finding here with the derivative of a line, it's just the slope of that line. Okay, anywhere we're at, the slope of that line is negative 5. So this one doesn't change.